Mathematically speaking, any object in the universe can become a black hole if you compress it into a small enough space. Every object has what's known as a Schwarzschild radius. Take the Earth. If you were to somehow crush the entire mass of our planet down to the size of a peanut, its density would become so extreme that its gravitational pull would trap even light. Luckily, there is no known mechanism to crush the Earth like that. But out in the cosmos, black holes form naturally when stars many times larger than our sun exhaust their nuclear fuel. Without that outward energy to fight against their own massive gravity, the core collapses in a fraction of a second, triggering a violent supernova explosion that leaves behind a completely dark, hyperdense sphere. Because we can't see them, pop culture often portrays these objects as roaming cosmic vacuum cleaners, sucking up everything in the galaxy. But their gravity actually works exactly like the gravity of any other object. Watch what happens if you were to swap out our sun for a black hole of the exact same mass. The Earth would certainly freeze in the dark, but its path through space would not alter. From a distance, a black hole's pull is identical to any other stellar body. Our frozen planet would simply continue orbiting that dark center, perfectly undisturbed. A black hole is completely harmless from a distance. The inescapable consequences only trigger if you make the choice to travel inward and cross its ultimate boundary. So let's take that theoretical one-way trip. As we approach the black hole, the very first thing you'd notice is the bizarre distortion of the starry sky ahead of us. This visual warping is caused by a phenomenon called gravitational lensing. The black hole's gravity is so intense that it bends the actual fabric of space, forcing light rays from galaxies millions of light years behind it to curve around the void before reaching our eyes. Because black holes themselves do not emit or reflect any light, astronomers rely heavily on this exact optical illusion. By scanning the sky for background galaxies that appear smeared and stretched into glowing rings, they can pinpoint the exact locations of massive objects that are otherwise completely invisible. To study these dark spheres, we are forced to look at the warped shadows and twisted reflections they cast onto the rest of the universe. Getting closer, we reach a region known as the Photon Sphere. Here, gravity is strong enough to capture light, but not quite strong enough to pull it inward. Instead, photons of light are forced into a perfect, infinite orbit around the black hole. If you were to stop right at this boundary and look to your side, you could theoretically see the back of your own head. Light reflecting off you would travel all the way around the sphere and right back into your eyes. Just beyond that optical illusion lies the event horizon. This is the absolute point of no return. Once you cross this threshold, the escape velocity exceeds the speed of light, meaning nothing can ever get out.
If a friend watched you fall toward this boundary from a safe distance, they would never actually see you cross it. Because extreme gravity heavily warps time, they would see your fall slow down. Your image would freeze in place, slowly turn red, and eventually fade into nothingness. But for you, falling inward, the experience is completely different. Looking back out at the universe, time dilation works in reverse. You would watch the future of the cosmos play out in extreme fast forward. By the time you cross that boundary, you are living in a separate timeline from the rest of the universe, watching the future unfold while your friends see you as a frozen relic of the past. Inside the event horizon, your survival depends entirely on the size of the black hole. The closer you get to the center, the more aggressive the difference in gravity becomes across tiny distances. Gravity would pull millions of times harder on your feet than on your head. Your body would be violently stretched vertically and squeezed horizontally, a gruesome physical process astrophysicists officially call spaghettification, tearing you down into a stream of plasma just one atom wide. Your remains would inevitably arrive at the singularity. This is an infinitely dense point where the curvature of space is so extreme that every possible physical direction you could turn only leads further inward. The singularity acts as a mathematical dividing by zero error in the fabric of reality. It is the exact location where our current laws of physics simply cease to function, leaving us completely blind to what happens next. At the center of almost every galaxy, we find supermassive black holes that have been feeding for billions of years, like TON 618, a behemoth holding the mass of 66 billion suns. But despite their terrifying scale and inescapable gravity, black holes are not eternal. As physicist Stephen Hawking demonstrated, they actually slowly evaporate over time. To understand how, we have to look at quantum mechanics. Empty space is actually filled with pairs of virtual particles that constantly pop into existence, only to immediately collide and annihilate each other. Watch the boundary closely. When this pairing happens exactly on the razor's edge of the event horizon, the rules change. One particle is pulled into the black hole, while its partner escapes into space, becoming a real particle. This escaping particle steals a microscopic fraction of the black hole's mass, a process known as Hawking radiation. It is an incredibly slow leak. The largest black holes will take a Google years to fully evaporate, surviving long after the last stars burn out and the rest of the universe goes dark. By combining the physics of the very large with the mechanics of the subatomic, black holes act as the only place where we can test how these two conflicting theories interact. They serve as the pressure points where we find the specific cracks in our current maps of the universe.